Now let's examine the three modes of radioactivity in some more details, meaning the alpha, beta, and gamma decays. First of all, there is an overview of how many types of decays are there and what are their prevalence. You have here a diagram plotting the radioactive and stable nuclides for a certain range of Z numbers, Z ranging between 65 and 80. That's a small portion of the elementary table. But you can see here, within this portion, this is the line of stability. Those black dots, each representing a stable nuclide with the right proportion of neutrons and protons. And each of these red ones represent an unstable nuclide, which will decay by emitting a negatively charged electron. So that's a beta negative decay. The reason why that's the case is because they have too many neutrons. You can see here, too many neutrons above that line of stability. And how to get neutrons, get rid of neutrons? By emitting a negatively charged electron. You can turn a neutron inside a nucleus into a proton by charge conservation, and that's how you become more stable. And those green ones, those ones do not have enough neutrons. So you see they're below the line of stability. They don't have enough neutrons. So they have to turn protons into neutrons by emitting positively charged electrons, or positrons. And the yellow ones are represent alpha decay. That's when you have you get rid of two neutrons and two protons in one gulf. That's an alpha particle. So this is an overview of how these three decays can exist in nature as a small portion of the elementary table. Now let's look at alpha, beta, and gamma decays separately. Let's look at some of the characteristics of each of these decays. Start with the alpha decay. Alpha, as we know, is the really the nucleus of the highly stable helium-4. Helium-4 means you have 4 nucleons in the helium nucleus, which means 2 protons and 2 neutrons. Helium-3, for example, has only 1 neutron and 2 protons. It is not nearly as stable as helium-4. So the alpha particle is made of helium-4, not helium-3, because being a very stable entity, it can escape as a whole. Now, conservation of the atomic number A and atomic number Z and atomic mass number A must be observed. The atomic number Z has to be conserved because that's the conservation of charge. Okay, the conservation of charge. What about the atomic mass number? Isn't it true that the mass is not exactly conserved because, some of the mass can be converted into energy and so forth? And yet the mass number A must be conserved. Why is that? You may wonder why that's the case. Well, it's because even though the total mass before and after the decay may not be exactly the same, we're talking about rest mass, only a very small fraction of the rest mass is turned into energy, or vice versa. And therefore, if you look at the number, this integer, which represents roughly how much mass there is, that number A cannot change. Okay? You can change the mass a little bit, but that's in decimal places. It does not affect that integer A. So A is still a conserved integer number. This is the generic formula for an alpha decay. You start with an element called X. That's called the parent nucleus. It's got this many nucleons and this many protons, A and Z. It emits an alpha particle. It emits an alpha particle. So A decreases by 4. So then it also emits a daughter nucleus, so-called daughter nucleus Y, and A becomes A minus 4 because you have to conserve A. And Z of this daughter nucleus becomes Z minus 2 because the other 2 is carried away by the alpha particle. So that's conservation of A and Z. That's the generic formula for that. An example is the uranium-238. The uranium-238 is the most abundant isotope of uranium in nature. It's got 92 protons and 238 nucleons. It's got a natural alpha decay process like this. This, in fact, is one of the many possibilities of alpha decay, this being an example for uranium-238. There are many other alpha decays, as you can see here. What is the typical energy released in an alpha decay? Otherwise known as the disintegration energy. Well, we can get that by comparing the rest masses before and after the decay. The energy before the total rest mass before the decay is mx, right? And the total mass after the decay is the sum of these two, the sum of these my and m alpha. The difference gives you the mass that's converted into energy. So you multiply this by c squared, or if you want to get the answer directly in MeV, you realize that when U equals this many MeV over c squared, so c squared itself equals 931.494 MeV over U. So you replace c squared with this, and then you write mx, my, m alpha in terms of U, as we usually do in nuclear physics, and what you get is just MeV directly. And Q, it's called disintegration energy. That is typically of the order of several MeV in a typical alpha decay. Now this Q is shared by the product particles. In other words, this daughter nucleus and this resulting alpha particle. They will both carry a certain amount of that energy away. They share that energy in terms of the kinetic energies of these two particles. And they also have to conserve momentum. Suppose you start with the reference frame, the inertial frame of the parent nucleus, so it's not moving. The momentum is 0 to begin with. After the collision, one particle goes this way, one particle goes that way. Their total momentum must also add up to 0 by conservation of linear momentum. So you have actually two conservation laws to observe: conservation of linear momentum and conservation of total energy. This total energy, kinetic energy released, is Q, shared by these two guys. So therefore, you have two equations and two unknowns. You can calculate what is the momentum carried by this one and momentum carried by that one. And from that, you can find the kinetic energy of this alpha particle, and it should only have one value. Okay, it should be a quantized discrete value determined by the conservation of energy and momentum. Let's see how that works. So let's start with this point number 2. These are the two prominent features of any alpha decay. We start with this. We'll continue with what we left out in the previous on the previous page. Quantized value of K alpha. What's K alpha? K alpha is the kinetic energy of the resulting alpha particle. Use the change of energy equal to 0, change of momentum equal to 0. Conservation laws. Okay. Here is the situation right after the collision, right after the split. The alpha particle is positively charged. The daughter nucleus is also positively charged because it's still got a lot of neutrons left, protons left, and they repel each other. Okay, so they fly away. This goes this way, this goes that way. P alpha and Py. The magnitude of P alpha should equal to the magnitude of Py because their total linear momentum should cancel out, just as before the collision, before the splitting took place, they had no linear momentum to begin with. So P alpha equals Py. That's the magnitude. Okay, again, the conservation of energy requires that the total energy released be shared as the kinetic energy of the alpha particle and the kinetic energy of the daughter nucleus Y. Now I'm going to use P over 2m, assuming that they do not move, neither of them move at relativistic speeds. That's a good approximation, in fact, because these guys are pretty light. Pretty heavy, pretty heavy. So they do not move near the speed of light. We can check that. Okay, so you have, you have these two equations, and we already, if equate these two P's, equate this and that, then we can actually solve for P. And then we get P alpha squared over 2m alpha. That is the kinetic energy, K alpha, that we're looking for. So you do this calculation, and you find that K alpha must equal to the Q value times this factor. This factor, of course, is less than 1, meaning that only a fraction of the final, of the energy released Q goes to the kinetic energy of the alpha particle. The remaining part goes to the daughter nucleus, which recoils that way. And that's a fixed value. Okay, the ratio m alpha, my over my plus m alpha, that ratio is fixed, and that ratio, by the way, is less than 1, but it's pretty close to 1, because the daughter nucleus typically has over 50. It's got over 50 nucleons, and this alpha has only 4. So this is pretty close to 1, which means the alpha particle must carry most of this Q value. Most of the energy released is carried away by the alpha particle in terms of its kinetic energy. At a typical value about 5 MeV. That's what we got for radon. The alpha decay of radon 226 produces an alpha particle whose energy is about 5 MeV, and that's fixed. That number is fixed for this particular decay because you have to observe this this expression. Okay, so when you look at the kinetic energy of the resulting alpha particle, you find that there is only one value. Now, another prominent feature of the alpha decay is something already discussed briefly before in an earlier chapter, in fact in chapter 41, quantum mechanics, when we discussed tunneling. This is a diagram for the potential energy of the alpha particle inside the potential well of the nucleus. This is inside the nucleus. This R is the size of the nucleus. So when you're inside the nucleus, there is a very negative potential well because of the strong nuclear attractive force. Attractive force corresponds to a negative potential energy. But right when you're above it, when you're outside of it, you have an alpha particle that's separated from the parent nucleus. They're both positive charged, so they repel each other. This is the 1 over R positive Coulomb repulsion potential energy between the alpha particle and the positive nucleus that it has left behind. Now, the alpha particle inside is initially trapped inside, okay, and it's got an energy it's got a kinetic energy about 5 MeV when it's already inside. How do we know that? Because after it gets out, when it moves, it still has 5 MeV. Okay, so when this alpha particle, when it moves to infinity, it's got energy 5 MeV. So basically that's what happened. It starts with this energy and it tunnels over this hump and it gets out with the same energy. That's what happens to it. Now the hump has a height of 30 MeV, so you have to scale over this fence. This is a totally quantum effect. Classically, this will not happen, as you know. Okay, unless you have this much energy, you'll never make your way out. But even the quantum tunneling is not easy. It depends on two things. Depends on how thick the barrier is. In this case, being at 5 MeV, you have to go all the way from here to there. You have to tunnel through this range, and you have to scale over this fence. Right? Now we learned that the probability of tunneling depends on two things. Depends on how tall a fence you have to scale and how wide a barrier you have to tunnel through, and both are exponential dependencies. We're looking at e to the negative 2 kappa x. Remember that? You go back to chapter 31. Okay. Now, if you have another alpha particle somewhere inside with a somewhat higher energy to begin with, so it's here, then it's got a double dose advantage. First of all, it has to go through a smaller or narrower barrier, and secondly, it has to scale over a lower fence. Since both are exponential dependencies, the tunneling probability of this guy is exponentially higher than the tunneling probability of that guy, which means this one would take a lot less time to get out. Okay? So, if you look at the half-lives of alpha decay, it's a very sensitive function of the kinetic energy of the alpha particle. If you have higher kinetic energy, that means you had higher energy to begin with when you're inside. So the tunneling probability becomes exponentially higher, which means it takes a lot less time for you to tunnel through, and therefore the half-lives would be dramatically lower. Take a look at this example. Okay, I have the two elements that I discussed before: 238 uranium and 226 radon. That's from the textbook. These examples. K alpha for uranium is 4.2 MeV. For radon, the resulting alpha particle has a kinetic energy slightly higher, 4.78 MeV. That doesn't look like a huge difference. It's about 5 MeV, as you can see here. Okay, the difference is only about less than 0.6 MeV, and yet look at the half-lives. Uranium-238 takes about 1 billion years to decay half of it. So only, in order to decay, it takes about 1 billion years, so half of the uranium-238 to decay, and yet radon takes only about 1,000 years. Only about 1,000 years. There is a 6 orders of magnitude difference. Why? Because this little small difference in K alpha results in an exponential difference in the tunneling probability going over this way or going over that way. This is a stunning example of how the quantum tunneling works, and that again was studied by George Gamow, the theory of alpha decay, which won him a Nobel Prize in physics. So again, these are the two prominent features of alpha decay. One is a quantized kinetic energy, a single value kinetic energy for the resulting of a particle, and secondly is the exponential dependency of the half-life of this radioactive alpha decay element on this value of K alpha. All right, now let's take a look at the features of the beta decay. There are two types of beta decays, beta positive and beta negative. So in a beta negative decay, you just end up with an extra electron coming out, and in a beta positive decay, you end up with a positron. Positron is a particle that looks every bit like the electron, with the only exception that it is positive charged instead of negatively charged. So these are the two generic formulas for beta decay. This is when you emit a positron, so the Z number decreases by 1. And this is when you emit an electron, so the Z number increases by 1. You have to conserve Z, conservation of charge. Now, the conservation of mass requires that the A number stays the same, because the electron or the positron, they each carry a very, very tiny fraction of the mass of a nucleon, about 1/2000. Therefore, even when you have an extra electron, the A number will not change. Okay? The A number will not change. So A is conserved, but Z can increase or decrease by 1 depending on whether it's positive or negative beta decay. The most striking feature of the beta decay is that the resulting kinetic energy of the beta particle is not discrete as the case of alpha particle. Okay? Alpha particle, you have discrete energy, as we just saw a minute ago. But the beta particle, it can have a range of kinetic energies, starting from 0, ending up at K maximum. Now this K maximum is as predicted, meaning that if you assume that the outgoing particles are this daughter nucleus and this electron, the positron, you use the same calculation that we did before a minute ago. You probably have to consider relativistic effect because the electron can travel at relativistic speeds, being so light. You can actually find the kinetic energy of the resulting beta particle, beta, be it electron or positron, and it actually agrees with this number. However, this is not the only value of the kinetic energy that this resulting beta particle can have. This is only its maximum value. Normally, it is lower than that value. It can be anywhere between here and there. So that means somebody must be carrying this excess energy away, right? And that suggests there must be a third particle somewhere here. That third particle obviously does not carry any charge because the Z numbers are conserved without its presence. And that third particle cannot be very massive, otherwise the A number will change. Right? So we're looking at a very light particle that's charge neutral. And the presence of this particle can explain this profile, because with a third particle, you have one more variable, which is the momentum of the third particle. Now, the incoming momentum is 0 if you use the reference frame of x. The outgoing momentum should add up to 0. So P1 plus P2 plus P3, okay, is 0. So you have that one equation. P1 plus P2 plus P3 equals 0. You have another equation, which is the conservation of total energy, which means the mass difference, the mass reduction between initial and final state should go into the kinetic energies of these three guys, K1, K2, and K3. Okay, so the reaction energy Q, whatever energy is released, is K1 plus K2 plus K3. But these are the only two equations we have. So you see, we have two equations, conservation of energy and conservation of momentum, but we have three unknowns, P1, P2, P3. So that means we don't have enough equations to fix what? To fix the momentum of the electron. Unless we kill this momentum in a rare event that this guy hardly has any momentum, and then we reduce that to the previous case before. So the presence of this third particle can explain this continuity of this curve, and this particle, being very light and charge neutral, was first proposed by Wolfgang Pauli in the year 1930, and he also coined a name for it. We call it the neutrino. Neutrino. Why the term neutrino? It means little neutral ones. Okay, means neutral. Okay, neutrino, it's called little neutral one. So let's take a better look at the properties of this new particle that we discovered called the neutrino. First of all, it's got no charge. And secondly, it turns out in order to explain this experimental profile that you saw here, the exact shape of this curve, you have to assume that the mass of the neutrino is zero, or more precisely, the rest mass of the neutrino is zero. So it's like a photon with no rest mass. And consequently, according to Einstein's theory of relativity, the speed of that neutrino must be equal to c, the speed of light. Any massless particle must travel the speed of light, right? I mean, look at energy equals gamma m c squared, right? M is zero. M is the rest mass. So gamma has to go to infinity, otherwise E is zero, which means the particle never existed. Okay, gamma equal to zero, which means V equals C. So you see, and that it reduces to PC. E equals PC if the rest mass is zero. This is the energy moment relationship, the so-called dispersion relationship for this relativistic particle. So besides photons, we know there is at least another type of particle that also travels the speed of light, and that's neutrino. At least that's the first assumption that people made in order to explain the properties of beta decay. I put a question mark here because there are debates going on as to whether neutrinos are truly massless. As a matter of fact, modern experiments put the upper limit of neutrino mass to about 7 eV, okay, not MeV, all right? The electron, as you know, is quite light compared with nucleons, and yet the rest mass of the electron is 511,000 eV. That's over 500,000 eV. Neutrinos, on the other hand, would have a mass less than 7 eV, over c squared, of course. So it's extremely light. Does that mean it doesn't have any rest mass? It is still an open question. There are experimental evidences that suggest that neutrinos may not be massless as we thought. It just has a very small mass, let's say 5 eV instead of 511 million, 511 k, 511 keV. But that 5 eV can go distances. It can explain a number of things, among which the so-called solar neutrino problems. The solar neutrino problem is an open problem in solar physics. That is, there seems to be a discrepancy between neutrino production that we calculated from the energy production of the sun. When we calculate energy production of the sun, which is by nuclear reaction, we found that in order to match the observed amount of energy released by the sun per second, we have to assume that this many neutrinos must be produced. And yet we have not detected as many neutrinos as we would hope that will coincide with the energy production rate of the sun, and we call that the solar neutrino problem. And one of the ways to resolve that would be to assume that neutrinos actually have a mass, rest mass, even though it's very, very small. Okay, and these experimental research is still going on, and today a lot of scientists do believe neutrinos may have a small mass, but how small is it? What are the consequences? It's still not entirely clear to people, so I put a question mark here. And it turns out there are different types of neutrinos. It's not the only single one. For all neutrinos are associated with what's called a weak interaction. There are two types of nuclear forces or nuclear interactions, the strong force and the weak force. So strong forces are between nucleons, okay, protons, neutrons, and so on. The weak force is involved in beta decay when there are electrons involved. Electrons are not nucleons. It belongs to another type of elementary particles we'll see in the last chapter of this course. But it turns out that for this type of particles called leptons, electrons being one of them, there is what's called a lepton number that you have to conserve in every reaction that's possible. And there are different types of leptons. Electron is the most famous one. Another well-known one is called muons. Muons are leptons as well. And when you have a decay involving the production or absorption of muons, there also has to be a neutrino associated with muons. And I put a bar here indicating that this is what's called an antineutrino. This is called an electron neutrino. This is called an anti-electron neutrino. They behave the same way except that they don't have the same lepton number. We designate a number of +1 for the electron, lepton number. To conserve lepton number, you must add a anti-electron neutrino every time you see an electron, because the anti-electron neutrino has a lepton number of -1. The positron is the antiparticle of electron, so therefore it's got a lepton number of -1. To balance that in a beta positive decay, you must also emit a electron neutrino with a lepton number of +1, which cancels with the -1 coming from the beta positive particle. These things will be discussed in more details later in the last chapter, particle physics. But suffice to say, there are different types of neutrinos. Okay, electron neutrino, muon neutrino. And again, neutrinos are present in so-called weak interactions involving such as beta decay. And the rest mass, as you know, we discussed that. How do I tell whether the neutrinos have a rest mass or not? Well, according to Einstein's theory of relativity, anything that has a non-zero rest mass cannot possibly travel at the speed of light. Just look at this formula. When m is not zero, no matter how small it is, gamma cannot be infinity, right? Because otherwise you get infinite energy carried by this single particle, which is not possible. So gamma has to be less than infinity, which means V is less than C. So, how do we know neutrinos have some rest mass? If it has a rest mass, it travels slower than the speed of light. And conversely, if we find that the speed of neutrino is less than that of light in vacuum, it must have some rest mass. What are the consequences? Well, the solar neutrino problem is one of them. And another thing we can think of is the total mass of the entire universe. Okay, the universe has what's called a critical mass, this concept associated with the universe. You know, the universe started with a Big Bang. Everything's expanding. But gravity is a force that tries to tie everything back together, right? One of the biggest questions that we ask in science is this Big Bang going to continue forever? Or is it ever going to stop at some point, and then everything comes back to a single point? It's called a big crunch instead of the Big Bang. Well, that depends on one thing, and that is, what is the total mass of the universe? You can calculate this mass, which is called a critical mass, such that if the total mass exceeds that critical mass, then there is enough attractive force among these masses. Eventually, the Big Bang will stop, the expansion will stop, and everything will shrink back. And if the universe has a mass that's lower than that critical mass, then the expansion will go on forever. So this, of course, is a big question, and the answer to that big question may lie in the property of the smallest of all particles, which is neutrino. And that is, if you give a tiny mass, say a few eV of mass to each neutrino, there are so many neutrinos in the universe that the masses of these neutrinos alone could actually propel the mass of the universe beyond the critical value, and therefore you can change the fate of the entire universe. This is unbelievable because we see here an example where the very smallest entity, the neutrino, can affect the fate of the very largest entity, which is the entire universe. No other branch of science other than physics can give us this kind of connection between the ultimate small and the ultimate large. But we'll see more of that in particle physics, the last chapter. But a recent development, supposedly by a group of physicists working at CERN, seem to suggest that some neutrinos can travel faster than the speed of light in vacuum. Now that's a totally different story, okay? If you travel a little bit slower, that is okay. That means, all that means that you have some rest mass, that's all. But if you travel faster than the speed of light in vacuum, how is that possible? That is a direct violation of Einstein's theory of relativity, right? And this is still an ongoing research, an ongoing debate, whether the experiment is actually foolproof And if it's perfectly executed, if the numbers are real, what does that mean? How should we rewrite relativity, and how should that impact our understanding of space and time? Again, most physicists believe that it's just an experimental error, but we cannot know for sure just yet. It's still an open question. Now, you may have seen the movie 2012. In that movie, supposedly, there was an explosion in solar neutrino activity. So the sun suddenly released a very high amount of neutrinos streaming towards the Earth, and that caused all kinds of problems. Now, I must tell you, this is total fabrication. This is pseudoscience. Okay, it's only for entertainment purposes. There is no science behind it. First of all, you cannot possibly imagine a situation where the sun can produce that many more neutrinos. And secondly, even if that were the case, we give it that. The sun produces, say, 100 times more neutrinos than would usually produce. Most of these neutrinos will stream through the Earth, our body, everything, the ocean, undetected. Neutrinos hardly, if ever, interact with other masses. It will cause no measurable effect. If the neutrinos by themselves, okay, will cause almost no measurable effect as they stream through the Earth, virtually undetected. The science behind this movie is totally wrong, as is the case with most science fiction movies. But the entertainment value, that's another story. All right, so let's look at some famous examples of beta decay. Here is a very famous example. If you have a neutron in free space, which means it is not locked up in a nucleus, okay? The neutron, turns out, in free space is not a stable particle, believe it or not. Neutrons are not stable in free state. It will decay into a proton plus an electron plus an anti-electron neutrino. You see the conservation law here? This electron has a lepton number of positive 1, and therefore it must be accompanied with another particle with a lepton number of negative 1, which is carried by the anti-electron neutrino, bar. Bar means anti. It's got a half-life of 930 seconds. That's not long at all, 930 seconds. Okay, so after 930 seconds, half of the free neutrons in air would die. So if a nuclear reaction released a whole bunch of free neutrons into the air, it's not a terrible hazard because most of these neutrons would die in a matter of minutes or at most hours. So they would become just harmless. And you can see here the rest mass of the neutron is somewhat greater than the rest mass of the proton, and the difference is a little over 1 eV, 1 MeV. I'm sorry, 939.57, 938.27. It's a little over 1 MeV, and that is enough to produce this half an MeV worth of electronic energy plus some more, plus some kinetic energy. So this reaction is energetically allowed to happen. Okay, so you can understand why the neutron has a little bit more mass than the proton. You can think of it as capable of producing an electron and turning itself into a proton.